Hi guys, hello, hi everybody. Welcome to Momentum with Vedantu, everybody. Today is the new class for class 11 students, JEE or NEET 2022 students. We are going to start the new topic today called kinetic theory of gases. We finished radiation in the last class, guys. If you haven't seen it, you can go and check it out. Today is the first class of the new chapter called kinetic theory of gases. It's an important chapter from NCERT as well as JEE point of view. The direct questions from this come on formula based direct questions also come from this chapter, and the derivation that we will do today is also very important, guys, because the advanced level questions can form based on that derivation. Okay, so that derivation is super important. Pay very close attention to that. Okay, in the meantime, let's say hello to all the students who are here. Vasudevan is here, Suraj is here, and who else is here? And who else is here? Atharva Sharma. Hi, Atharva Sharma. Welcome, Darth Vader. Everybody's here. I'm Mahinder Pal. Hi, everybody. How are you guys, by the way? How are you? Can you hear me properly? First of all, you have to tell me in the chat if you can hear me properly. Can you give me a thumbs up if you can hear me properly? Surinder Singh is also here. Very good. Yes, Ayush Vale. This is a theory-based chapter, but the one super important derivation in this chapter, because all the advanced level questions that you will see will come from that derivation. Okay, so all right, hi Abhyuday, Surinder Singh, everybody can hear me. Okay, awesome guys, awesome. So let's start today's class. We'll begin now. But before we do that, let's talk about the person who gave the answer first. Okay, who gave the answer first, guys? Who was the first person who gave the answer in the last class? Who was it? Who was it? Can anybody guess? Can anybody guess? Can anybody guess? Is he here first of all? It was a smart book. Is smart book here or not? Smart book here or not? Smart book? Oh yeah, smart book was the first person to give the answer. Very good, smart book. Very good, very good. Yeah. He already knew that he gave the first answer. हाँ वहीं पे इसने लिख भी दिया था. Yo, first answer me. Hooray! Awesome, awesome. All right, so very good, smart book. Okay, Hina, I just missed it. It's okay, Hina. No issues, no issues. Let's start today's class. Okay, yay! Smart book is also here. Awesome. Hi, Shivas Prabhu Desai. Superb, superb. Okay, Ran Faris. I know your pain, my friend. I know your pain. But we want to do some one-shot classes. Okay, we will do that. We'll do that, and then we'll go back to the normal schedule. Okay. Anyways, guys, let's start today's class. Let's start today's class. It is going to be kinetic theory of gases. Okay, kinetic theory of gases. Now, what exactly is kinetic theory of gases? Basically, Anna, these are the set of assumptions. Okay, set of assumptions that we made for an ideal gas. Okay, that we made for an ideal gas. Okay, so this is where this chapter starts. We talk about a few assumptions in case of an ideal gas, how it is supposed to function, how it will look if you enlarge the view, if you go at microscopic level, how things function. Okay, so that exactly is kinetic theory of gas. Okay, yeah, exactly. Ayush Vale is describing kinetic theory of gas with just one letter. At the end of it, guys, we always come towards this function PV is equal to nRT. Okay, but before we get to it, there are a lot of things that we have to get through. Okay, there are lots and lots of things that we have to get through. So we'll do that. Okay. Pradyumna, this lecture is enough for JEE Mains and NEET. For advanced, we will need to do some extra stuff that I'm not covering in this lectures, because you see, we are doing this in a very little time frame. So I cannot cover advanced level right now, but we will have advanced lecture series later. Okay, don't worry. All right. Okay, yeah, Kritika Biswas, this is the repeat of chemistry. We have studied this already in chemistry in class 11th. Okay, I think in 11th only. Correct? Solid states of matter. Correct. Very good, very good. Okay, sure. So let's start with this. Okay, so first of all, there are certain postulates. Okay, there are certain postulates of kinetic theory of gases. Now, guys, postulate is an English term, and the meaning of this word is basically this is just we are saying that this is true, Okay, whatever we are going to say now, we are saying that that is true without giving any proof for it. Okay, such a thing is called a postulate. Like, I know that this is true, but I don't know why exactly. Like, I'm not going to give you proof for it. So that is called a postulate. Okay, so what exactly is postulate for ideal gases? So what we say is that, first of all, let's say I have a container, and inside this container I have ideal gas. Okay, inside this container I have ideal gas. So that is going to look something like this. Now in this case, guys, in this case, if you see, am I buffering? Yes, I'm buffering for myself as well. I'm buffering for myself as well. I don't know. Yeah, now everything is okay. Now I think everything is okay. All right, so if you see here, all the molecules are going to move randomly in all directions. All the molecules are going to move randomly in all directions, and not all of them are going to have the same speed. Okay, all the molecules mostly going to move with different speeds in different directions. Okay, they are going to randomly move in different directions at different speeds. Okay, that is the first postulate. That is the first thing that we are going to say is true. Okay, this is the first postulate of kinetic theory of gas. What is the second postulate of kinetic theory of gas, guys? This once again is an assumption, or this is a fact that we are saying. Okay, and what is that? That the size of the molecule of the gas, when the gas is moving in the container, the size of the molecule of the gas is much smaller than the average separation of molecules. Okay, size of molecule of the gas is much smaller than separation between the molecules. Okay, if you take this size as d and separation as capital D, then d is going to be much larger than small d. Okay, the capital D is going to be much larger than small d. Okay, yes, the gravitational effect. So we that's another postulate, that we ignore the effects of gravitational force. Okay. The second thing is, the third postulate is that the molecules exert no force on each other. The molecules exert no force on each other or on the wall of the container except during collision. Now, guys, this thing I know for a fact is not true. Everybody knows this is for a fact not true. All the molecules are going to feel gravitational force between each other, gravitational force between the wall and the molecules, and gravitational force between the molecules and the earth. Okay, but we are going to ignore all those forces and just go with the assumption that there are no force between the molecules except the force during the collision. Okay. Ayush, I do not shave, I do trimming, I will do that. Okay. Harneet, yes, I know. I will do that. I will do that. The timetable we are going to change very soon. Okay. Now, next postulate. Okay, these are all important assumptions that we are starting with, guys, and these are important not because, like, for you, just assume that these are just properties of ideal gases. Okay, these are just properties of ideal gases. Okay, next important thing, guys, whenever a molecule collides, okay, a molecule can collide with other molecule, or a molecule can collide with the wall. Whenever a molecule collides with either another molecule or the wall, that collision is perfectly elastic. That collision is perfectly elastic. Now, I don't think you guys have studied elastic and inelastic collisions yet. That comes in the chapter center of mass. But for now, just assume this. What exactly is an elastic collision? If a molecule is coming with velocity v, then after collision it will again go back with speed v. Okay, in this case, in case of elastic collision, basically there is no loss of kinetic energy during collision. No loss of kinetic energy during collision. Such a collision is called an elastic collision. Also at the same times, okay, the collision time, the time during the collision, okay, the collision are supposed to be considered instantaneous. Okay, they do not take any time to do the to collide. Okay, it's just going to be an instantaneous collision. Now, next is next is that the molecules obey Newton's laws of motion. Okay, and here, by the way, by Newton's laws of motion, we talk about the first, second, and third law of motion. Force is equal to mass into acceleration, and all of that. Force is equal to mass into acceleration, and all of that. Okay, guys. So based on this, I want to ask you one very simple question, which I think you guys should be able to solve. Which I think you should be able to solve, and that is this. Tell me the correct answer, guys. It's a theoretical question. Tell me the correct answer. Hi, Shravani. Yes, I will, Shravani, I will share the notes. Don't worry. Okay. Mm. Mm. Tell me. Pa, 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 pa. Which of the following statement is wrong? So, which of the following statement is wrong, guys? I know you know. Just give me the answer. Which statement is wrong? Which statement is wrong? Okay, guys. See, the thing is, the last statement feels like it's a new type of a statement, and we don't know what it is exactly. But this statement is correct. Okay, this is not a wrong statement. The momentum is conserved during collision is also correct. That is true for any type of collision. Okay, and since our collisions are elastic, the kinetic energy is also conserved during collision. This statement is also correct. The only incorrect statement here, guys, is this: the kinetic energy is lost in collision. So the correct answer of this statement is going to, the correct answer to this question is going to be A. Hi Ajay Acharya, high five Ajay Acharya, high five. Okay, now so when there was this guy whose his name was Maxwell, okay, and Maxwell, guys, was very much obsessed with these ideal gas and movement of gas molecules within ideal gas. Okay, now whenever gas molecules are moving inside this container, guys, what will happen is that all of them will move at different speeds. Okay, not all of them are going to have the same speed. Now, by the way, here we are talking about billions and trillions of molecules. Okay, one mole of gas is basically 10 power 23 molecules. So that's a lot of molecules, and all of them will have kind of different velocity. Okay, not all of them will have same velocity. It's not impossible for two molecules to have the same velocity, but in general they will have different velocities. Okay, Maxwell was obsessed about this, and he wanted to figure out that, okay, with what velocity what molecule is going to move, with what velocity what molecule is going to move. Okay, now the thing is we can't just look at all the molecules individually, guys. We cannot look at all the molecules individually. Why we cannot look at all the molecules individually? Because there are just not so many molecules. 10 raised to the power 23 molecules, that's a lot of molecules. Okay, अगर एक एक मॉलिक्यूल को एक एक बाइट का डेटा दे दिया फिर भी that's 10 raised to the power 23 bytes. That's a lot of bytes. Okay, that is like टेरा से भी ऊपर पेटा पेटा बाइट चला गया. Okay, that's a lot of information. You can't study all the molecules individually. So what you can do is you can study this statistical. You can study this statistical. Okay. Statistically is basically we are going to look at it from above, from the outside. We are looking at the average velocity of all the molecules. We are looking at the most probable velocity, median velocity, this velocity. All those things we can study, but because the number of molecules is so large, we cannot just follow an individual molecule and see where it is going and where it is not going to go. Okay, because that is just too complicated. Okay, here if you feel that this picture is too complicated, here we barely have 20 to 30 molecules inside this container. Okay, if you go and imagine 1 trillion molecules inside this or one mole molecule inside this, it becomes super complicated. So we can only study this statistically, and that is what Maxwell did. Okay, that is what Maxwell did, and he came up with a law. That is what Maxwell did, and he came up with a law, and that law is called Maxwell's speed distribution law. That law is called Maxwell's speed distribution law. Now, first of all, you do not need to no need to remember this. Okay, no need to remember this is basically, this formula is out of syllabus, so we don't need to worry about this exactly. Okay, but I just wanted to show you this formula to show you that how complicated this is. Okay, how complicated this is to understand. how complicated this formula is and how Maxwell might have come up for it through came up with this formula. I don't know. Okay, but if you see this formula and you start plotting a graph, interesting features of that graph will emerge. Okay, and what we will do is we will study the graph which is represented by this formula. We will study the graph represented by this formula. Okay, so let's try to understand that. Okay, let's say, guys, let's say I have a container. Let's say I have a container, and inside this container I have some amount of ideal gas, and all the molecules of this ideal gas are moving in random directions. Okay, I do not know which direction they are exactly moving in, so I will just guess and make these directions. Okay, all the molecules are moving in random directions with random velocities. Okay, this was moving with speed v1, speed v2, speed v3, speed v4, speed v5, speed v6. Okay, and speed v7. Okay, so there's so many molecules, all of them moving in various different directions. We don't care, whatever. Okay, but what we will do is we will make a graph of the speed distribution for all these molecules. Okay, and exactly what am I making here, so basically I'm going to draw a graph between number of molecules. I'm going to draw a graph between number of molecules and velocity of those molecules. Okay, number of molecules and velocity of those molecules. Okay, so what are you talking about? What? Okay, by the way, you are able to hear me properly, right? I hope you are able to hear me properly. Okay, so what exactly this means, let's say I look at the molecules inside, and what I find is that there are zero molecules having 0 meters per second velocity. There are zero molecules inside having 0 meters per second velocity. So what I will do is, correspondingly, I will mark a point here. I will mark one point here corresponding to 0 and 0. Also, at the same time, I realized that okay, there are five molecules here with velocity of 100 meters per second. There are five molecules. There are a lot of molecules inside, but five of them have velocity of 100 meters per second. So what I will do is, correspondingly, I will mark a point here. Okay, 5 on the y-axis and 100 on the x-axis. Okay, then I analyze this some more, and I realize, oh, there are 10 molecules inside with velocity of 200 meters per second. Okay, so I will mark another point here. Okay, I will mark another point here with 10 on y-axis and 200 on x-axis. Okay, guys, I hope everybody is following so far. I hope everybody is following so far. Okay, Spaceman is asking, sir, how fine? Are Spaceman, this is experimental data which I'm explaining, and I'm explaining how the graph comes. Okay, this experimental data, experimentally I measure the speeds of every molecule, and this is what I get. And based on that, I'm trying to make the graph. Okay, all right, Spaceman, this is experimental data, my friend. I'm explaining the experimental data here. Okay, also at the same time, guys, let's say I got that there are 15 molecules with a speed of 300 meters per second. So once again, I will plot that graph. That will be somewhere around 15 here. Okay, blah 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 blah, one point mentioned here. Okay, then I keep plotting this graph. Okay, once again I get that okay, there are 12 molecules with a speed of 400 meters per second. Okay, so I will plot another point here. I will plot another point here. 12 molecules with a speed of 400 meters per second. Then I got that oh, there are basically 8 molecules with a speed of 500 meters per second. Okay, chalo. Anyways, I will plot another point here. 8 molecules with a speed of 500 meters per second. So on and so forth. I will Yeah, these are rough numbers. These are just data to give you an idea. Okay, do not note down these numbers. These numbers are not real. These are just numbers to give you an idea. Okay, so and let's say there are let's say three molecules with a speed of 900 meters per second. Okay, so I will mark one more point here. The 900 will be somewhere far away, but only three molecules. And like there is also one molecule with a speed of there's also one molecule with a speed of 2500 meters per second. Okay, so there will be one more molecule somewhere here. Okay, so now once I plot all these points, guys, once I plot all these points, what I will do is I will just join all of them. Okay, I will just join all of them and I will get a graph something like this. Just to join all of them and I will get a graph something like this. Okay, now the thing is, do not remember this data. Okay, do not remember this data. Remember the shape of this graph. Remember this shape of this graph. Do not remember this data. This data is not important because anyways we don't have very few molecules. We have billions and trillions of molecules inside. Okay. Oh my God. So do not remember this data, remember the graph, remember the shape of the graph. Okay, that shape of the graph looks something like this. Guys, this graph has a special name. This is called Maxwell distribution curve. This graph has a special name called Maxwell distribution curve. Okay, this curve is called Maxwell distribution curve. Let me draw a more beautiful version of this curve because this one is, let's be honest, it's a little bit ugly. Okay, so let me draw a more beautiful version of this curve. It will look something like this. Right? It will look something like this. Ooh. Okay, something like this. Nope. I'm sometimes not satisfied with my own drawings, right? So we will get it right. Until then, we cannot move forward. Okay. Yeah. Okay. So this is the graph. Okay, this is the graph that we see. You have to understand the meaning of this graph. Now guys, when you look at this graph, there are certain things that you have to notice. There are certain things that you have to notice. That first of all, there are very few molecules with low velocity. Few molecules with low velocity. Okay, low speed, not velocity, let's call it speed, low speeds. Okay, there are few molecules inside this container which are going with low speeds. And there are very few molecules having very high velocity. Okay, few molecules have very high velocity. Few molecules, okay, have high speeds. But if you see, most molecules have speeds somewhere in the middle region. Most molecules have speeds in between, in the middle region. Can you see that? Can you see that? And this is basically, this graph essentially represents a lot of things in your normal life as well. If you look at the entire population of your class, okay. So in the entire population of the class, there will be a very few students. There will be very few students who always score very high marks. Okay, there will be very few students who always score very high marks. We call them Maggu students. Okay, and also at the same time there will be very few students who score very low marks. Okay, most students in your class are going to be in that in between range. Okay, so this is basically how life also works in general. But if you look at gas molecules, this is how gas molecules are also there. Okay, inside the gas molecules also these type of things happen. Okay, I hope everybody understood. Now, guys, what would happen if I make changes to this system? Okay, what would happen if I make changes to this system? Okay, so let's say I am like, no, guys, I am going to double the number of molecules inside this container. Okay, I thought, okay, so I am going to double the number of molecules inside this container. So in that case, how do you think the graph will change? In that case, how do you think the graph will change? In that case, the graph will change something like this. In that case, the graph will change in something like this. Now here, what do you see, guys? Here, what do you see, guys? That for each speed, the number of molecules, for each velocity, the number of molecules increase, but overall the distribution still remains the same. Overall the distribution still remains the same. Here, what have I done? Here I have molecules doubled. Here I have number of molecules doubled. Okay, imagine I had done something differently to this container, guys. Imagine I have done something very different to this container. Instead of doubling the number of molecules, I had doubled the temperature. If I had doubled the temperature, okay, so what would have happened in that case, guys? If you increase the temperature of the gas, then what will happen? All the gas will start moving more faster in all directions. Okay, if the temperature of the gas is increased, then what will happen? All the molecules will start moving faster in all the directions, and in that case the graph might change to something like this. In that case the graph might change to something like this. Do you understand what happened here, guys? Do you understand what happened here? Here I have temperature increased. Okay, if I increase the temperature, what is going to happen? Speed of each molecule is going to increase, and the graph will shift a little bit towards the right. Okay, now what you have to understand here is, guys, that in all these three cases the shape is going to remain the same. In all these three cases the shape of the graph is going to remain the same. See, the shape always looks something like this. It's not going to happen that okay, I increase the temperature a lot and the shape changed to something like this. Okay, the shape of the graph is always going to look like this, and this special shape is called Maxwell distribution curve. This special shape is called Maxwell distribution curve. Do you guys understand this? Do you understand? Yes, Ratnesh, of course I remember you. I of course remember you. Okay, every time you change something, the graph might go up, the graph might go a little bit towards the right or left. It doesn't matter. The shape is always going to remain the same, and it is going to remain. That shape is called Maxwell distribution curve. Okay, now let's understand the features of Maxwell distribution curve. Okay, let's understand features of Maxwell distribution curve. Let me just remove all these once again. Okay, no need for them right now. No need for them right now. Now, in this case, guys, what you see is that there are certain molecules. Okay, there is a certain speed. There is a certain speed which is there for most number of molecules. There's a certain speed which is there for most number of molecules. Do you see that? Do you see that? What do you think that speed will be called? What do you think that speed will be called? That speed, guys, is called, that speed has a special name. It's called VMP. Okay, VMP. What exactly is VMP, guys? VMP is called most probable speed. It is called most probable speed. Okay, why is it called most probable speed? Because most number of molecules have that speed. So if you just pick out a molecule at random, the probability that it will have this velocity is highest. The probability that it has this velocity is highest. This is called most probable speed. This is called most probable speed. Okay. Now, secondly, if I have a lot of molecules inside, guys, then I can also do something else to these molecules. Okay, what can I do? What can I do? What can I do? I can also take, I can also take average speed of all molecules. Okay, I can also take average speed of all molecules. What exactly is average speed of all molecules, guys? What exactly is average speed of all molecules? It's basically V1 plus V2 plus V3 plus V4 plus dot plus Vn whole divided by n. Okay, let's say the number of molecules inside is capital N. So I have to add all the velocities and then just divide it by n. Now, Maxwell did that mathematically. Okay, Maxwell did that mathematically on his equation. He used this equation to find out the average velocity of all molecules. Okay, the maths is very much out of our syllabus, so we will not worry about that. He calculated this average velocity, and what he realized is, guys, what he realized is that because I have some molecules here which have very high velocity, because I have some molecules here which have very high velocity, they are increasing the overall average velocity of this gas. And basically what Maxwell got is that the average velocity was a little bit more than the most probable velocity. The average velocity was a little bit more than the most probable velocity. We have is called average speed. Okay, it's called average speed of all molecules. Okay, I hope everybody understood. It's not average velocity, guys. It's average speed. Okay, don't average velocity is vector sum of all the molecules, all the velocities. We are doing just magnitude sum and divided by. Okay, so it's called average speed. Okay, then finally, after this, Maxwell was still like he still had to calculate one more quantity. Okay, he still had to calculate one more quantity, and this statistical quantity has a very different name. This statistical quantity is called RMS velocity. Okay, he wanted to calculate something called RMS velocity. What exactly is RMS velocity, guys? What exactly is RMS velocity? One second, let me write that in green. He calculated VRMS. Okay, RMS stands for, guys, RMS stands for what? Root mean square velocity. Root mean square velocity. Okay, so he finally calculated the third type of velocity called RMS velocity. And if I have to define RMS velocity, guys, what exactly is RMS velocity? Okay, so basically, whatever is written, you have to go in the reverse order of that. Okay, whatever is written, you have to go in the reverse order of that. Okay, so first of all, we will take all the velocities v1, v2, v3, dot dot dot, vn. We will take all the velocities. Okay, then the first thing we will do with them is we will square all the velocities. Okay, so when we square all the velocities, guys, it will be v1 square, v2 square, v3 square, dot dot dot, vn square. Then the next thing we have to do is we have to take the mean of all those square velocities, or basically we have to take average of all those squared velocities. Okay, so we will just add all the squared velocities and divide it by number of molecules. Okay, that will be the mean of all the squared velocities. And finally, what do we have to do? Finally, we have to take under root of this mean. So finally what we will do is we will just take under root of all these mean velocities. Okay, remember this n here is inside the under root. Okay, the n, the number of molecules here is inside the under root. Okay, it's a small detail, but remember that detail. Okay, inside the root. Okay, so Maxwell calculated this as well using a lot of maths, and when he did, what he realized is that this RMS velocity was even bigger than the average velocity. The RMS velocity was even bigger than this average velocity. Okay, RMS velocity is even bigger than this average velocity. Now he calculated all of this using his formula. Okay, he calculated all of these using this formula, which it's out of our syllabus, so we will not get into calculation of those velocities. But when he calculated, guys, he got three different formulas. And what I am going to do, guys, I'm just going to give you those three different formulas. Okay, so what he got is he got the most probable velocity as under root 2p divided by rho. Under root 2p divided by rho. Okay, what exactly is p here, by the way? What exactly is p here? P is the pressure of the gas and rho is the density of the gas. Okay, and he calculated using his superhuman mathematics. He also calculated the average velocity. Okay, one second, I didn't change the color. He also calculated the average velocity, and when he calculated the average velocity, guys, what he got, this formula once again is very weird. So remember this, it's under root of 8p by pi rho, under root of 8p by pi rho. Okay, And finally he also calculated the RMS velocity. Finally he also calculated the RMS velocity, and the RMS velocity when he calculated, he got it as RMS velocity when he calculated, he got it as under root of 3p by rho, under root of 3p by rho. I hope everybody understood. I really hope everybody understood. Now guys, if you see here, all these velocities have a fixed ratio with each other. All these velocities have a fixed ratio with each other. If you take their ratios, what will be their ratios, guys? What will be their ratios? It will be under root 2 is to under root 8 by pi, okay, is to under root 3. Under root 2 is to under root 8 by pi is to under root 3. Okay, all these velocities are in this ratio. And the derivation of all the three velocities is not in our syllabus. The derivation of all the three velocities is not in our syllabus. But what we will do is we will try to derive one of them. We will try to derive one of them. Which one will we try to derive? Which one will we try to derive? We will try to derive the VRMS velocity. And this is the derivation that I'm going to do now. Okay, this is what we will derive. This derivation is part of our syllabus. All the other two velocities derivation is not part of our syllabus. Okay, and this one also, guys, we will not derive using Maxwell's distribution law. No, we will not derive using that. We will derive it using something else. Okay, we will derive not using Maxwell's distribution laws. We will derive it using something else. Guys, if you followed everything so far, please give me a thumbs up. If you followed everything so far, please give me a thumbs up. Okay. Mm. No. Thumbs up, thumbs up. Okay. Entertainment 2015, most of what we are doing today is CBS, NCRT level things. So yes, NCRT में जो भी होता है, everything is very very important for NEET. So yeah, very important, very important. Yeah. Alright. So next, let's talk about calculation of pressure of an ideal gas. Basically, we are going to try to calculate the RMS velocity of a gas. Okay, we are going to try and calculate the RMS velocity of a gas. So in this case, guys, in this case, you know what? Let's just remove this. I don't like this. You go. Okay, you go. Yeah. So in this case, guys, let's say I have a small container. Okay, let's say I have a small container. Okay, and this container is cuboidal in shape. Okay, it's a cuboid in shape. So let's say this length is equal to A, this height is equal to B, and this breadth is equal to C. These are the three lengths, A, B, and C. This is a container, cuboidal container. And let's say inside this cuboidal container, I have one molecule. Okay, I have one molecule which is moving in a certain direction with certain velocity. Okay, now it's moving in a random direction with some random velocity. Okay, let's say the mass of the molecule is equal to m. Okay, mass of the molecule is equal to m. I hope everybody is following so far. Now, therefore, if it has a moving in random direction with random velocity, it will have three components of velocity. It will have component in x direction, it will have component in y direction, it will have component in z direction as well. Okay, but here for the sake of simplicity, what I will do is, for you know what, let me just make all of them. Okay, Vx, Vy, Vz. Because the molecule is moving in 3D space, it will have velocity in all the three directions. Okay, but for the sake of simplicity, we will only study one for now. Okay, but if I ask you what is the value of speed v, so you can say it is going to be nothing but magnitude of Vx square plus Vy square plus Vz square. Okay, this where am I writing this from? Where does this come from? This comes from vector. Okay, this comes from vectors. The total speed will be square sum of individual speed, individual components. Okay, that comes from vectors. I hope everybody knows that. Okay, but here guys, what I will do is to make things simple because things are super complicated right now. What I will do is I am going to observe this. I am going to observe this from right here. I am going to observe this entire system from right here, and I'm trying to look at velocity only in one direction, which is the x direction. Is the molecule moving only in x direction? No, it's moving in all x, y, and z directions. But for now, to understand this, I'm going to look at its motion only in x direction. It's actually moving in y and z direction as well. I am just not going to look at it for now. Okay, so if I look at it from this observer's point of view and only look at the x direction velocity, what will I get, guys? What will I get? I will get a picture which looks something like this. I will get a picture which looks something like this. I will have, instead of a cube now, because I'm looking at it right from the front, I will just look at a square. Okay, this is also actually coming out of the plane of the paper, but right now it will, because I'm looking, my viewpoint is exactly in this direction. I will just look at it as a square with length as A and breadth as B. Okay, this is how it will look. Can you see that? Can you see that? Can you see that? Can you see that? I hope you guys can see that. I hope you guys can see that. And let's say the molecule is inside here and it has mass m and velocity vx. Okay, and velocity vx. It has velocity vy and vz as well. I am not going to look at it right now for now. Okay, now what happens is, guys, now what happens is that when you have a molecule like this molecule is going to, this molecule, you know what, I'm going to use a blue pen. This molecule is going to go on a path like this and then collide with, this molecule is going to collide with the wall. Okay, and then come back. Now when it comes back, it will again have mass m only. It will still have mass m only, but this time its velocity will be vx in the backwards direction. Will it lose any velocity? No, it will not lose any velocity. No, it will not lose any velocity. Why will it not lose any velocity, guys? Because we are, it, the collision is elastic. Okay, guys, if you are just joining us, we are deriving the vrms velocity for a molecule of an ideal gas. Okay, so what will I write? I will write that the momentum, okay, of molecule, momentum of molecule before collision, before collision. What will be the momentum of the molecule before collision? What will be the momentum of the molecule before collision? I will write it as Pi, and that will be equal to mvx. Pi, initial momentum, and it will be equal to mvx. And if I want to write it in vector form, I will write it as mvx I cap. Okay, similarly, if I had to write the momentum of the molecule after collision, then what will be the momentum of the molecule after collision, guys? Can you guys tell me in the chat? Can you guys tell me in the chat? I know you know. I know you know. Just tell me in the chat after collision. Ah, spaceman is correct. That will be minus mvx. I get. Why the minus sign, guys? Why the minus sign? Because now the molecule is moving towards negative x direction. I hope everybody understood. Yeah, superb, superb, superb. Now, from this, guys, if I ask you what will be the change in momentum? Okay. By the way, Momentum with Vedantu is the name of this channel. Okay, just in case you forgot. If I ask you what is the change in momentum, what will be the change in momentum? What will be the change in momentum? The change in the momentum will be PF minus PI. Pf minus Pi, which if you calculate will be minus 2 mvxi cap, minus 2 mvxi cap. Now, guys, this is where you have to understand a few things. Okay, this is where you have to understand a few things. Now, see, this is the wall. Okay, and the molecule comes and hits the wall. Molecule comes and hits the wall. Every time it hits the wall, what happens is that the momentum of the molecule changes. Momentum of the molecule changes. But where does that momentum go? Where does that momentum go? Basically, what the molecule is doing is whenever it collides, it is transferring its own momentum to the wall. It is transferring its own momentum to the wall. Do you understand? Do you understand? Because of law of conservation of momentum, because of law of conservation of momentum, the momentum that decreases for this molecule will be same as the increase in momentum of the wall. The wall will feel a transfer of momentum. The wall will feel a momentary force in positive x direction. Okay, I hope everybody understood. Okay, so what I will do is I will talk about change in momentum of the wall. Okay, if I ask you, go, 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 go. Okay, change in momentum of wall. If I ask you how much will that be, the change in momentum of the wall will be plus 2 mvxi cap. Okay, where does this come from? This comes from law of conservation of momentum. Okay, law of conservation of momentum. If momentum of the molecule is decreasing, momentum of the wall is supposed to increase. The total momentum has to remain constant. Okay, this is where it comes from. I hope everybody is following. Guys, this is a very important derivation. Okay, so everybody has to pay attention. Everybody has to pay attention. Now, in this case, if you see a molecule is going to not just collide with this wall once. Okay, molecule doesn't collide with this wall just once. It's going to collide with this wall again and again and again and again and again. Okay, why? Because once after the collision, the molecule starts from here, it will go up to this and then come back and then collide again. Then it will go again back and then come back and then again collide. Then it will go back and then come back and then again collide. Then it will go back and then come back and then again collide. So the molecule is going to collide with this wall over and over and over, not just once, over and over and over. Okay, so if I ask you a very simple question that I am going to ask you, what is the time period? What is the time period between two successive collisions? What is the time period between the two successive collisions? Okay, so can you tell me how much time period will be there between two successive collisions? Tell me. Arey, Kaushik, board aayega. Don't worry about the board. Board will come. Don't worry. Okay, so what will be the time period between two successive collisions? Guys, tell me, yeah, tell me. You guys should know this. You guys should know this. See, after one collision, the molecule will go like this and then come back like this and then collide again. So how much distance is it totally traveling? How much distance is it totally traveling? Can you tell me how much distance did it travel? It traveled a total distance of 2a. It traveled a total distance of 2a. And with what speed did it travel that distance? What speed did it travel that distance? It traveled that distance with the speed of Vx. Okay. Now I don't know if you guys know this. It's a very simple thing. Well, I don't know if you guys know this, but there's an equation in physics. Oh, ho, 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 ho. एक second, huh? There's an equation in physics called speed is equal to distance upon time. Do you guys remember? Do you guys remember? Which gives me time is equal to distance upon speed. Okay, in this case, if I ask you how much is the time period between the two successive collisions, then that will be equal to, guys, 2a, the distance traveled divided by vx. 2a divided by vx. I hope everybody understood. I hope everybody understood. I hope everybody understood. Okay, now everything has to be clubbed together. Okay, so guys, what I will say is that every time the molecule collides with the wall, every time the molecule collides with the wall, it imparts 2 mvx momentum onto the wall. Okay, every time it collides, it imparts 2 mvx molecule. Then after some time it collides again, then again imparts 2 mvx momentum. Then it collides again 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 2 mvx momentum. Yes, do you understand? So what I can say is that on an average, this molecule is applying force on the wall. Okay, and if I ask you what will be the average force on the wall, what will be the average force on the wall due to this molecule? So you can say that the average force is going to be nothing but change in momentum by time taken. Okay, if you remember Newton's second law of motion, force is equal to change in momentum upon time. I hope everybody understood. Everybody understood. Okay, which is just going to be 2 mvx divided by 2a by vx. Now, if you see here, 2 and 2 will get cancelled out, Vx and Vx will get multiplied, and I get the average force as equal to mvx square divided by A. I get mvx square divided by ai. Now guys, this is where we now stop talking about just one molecule. This is the force on the wall. This is the force on the wall due to one molecule. This is a force on wall. Okay, force on wall due to one molecule. Okay, but as far as we know, guys, is there only one molecule inside this container? Is there only one molecule inside this container? No, there are lots and lots and lots of molecules inside this container. Okay, let's say the total number of molecules inside this container is n. Okay, so what can I say, guys? What can I say? If in this case I want to calculate the total force on the wall, if in this case I want to calculate the total force on the wall, what will I say? Total force due to all molecules. Then what will that be, guys? What will that be? The total force due to all molecules, guys, will be equal to force due to the first molecule, which will be mv1x the whole square divided by A, plus force due to the second molecule, mv2x the whole square divided by A, plus force due to the third molecule, mv3x the whole square divided by A. Similarly, we will keep adding on force due to each and every molecule, guys. We'll keep adding on force due to each and every molecule. What will that be? So I will just write it as dot 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 plus mvn whole square, mvnx the whole square divided by A, where V1 is the velocity of first molecule, V2 is the velocity of the second molecule, V3 is the velocity of third molecule, fourth molecule, and nth molecule. All the molecules' velocities are added together. Okay, if I want to write this, guys, in a normal form, I can just write the force is going to be just equal to, the force is going to be just equal to what? The force is going to be just equal to m by a into sigma vix the whole square, where I goes from 1 to n. Okay, this is a statistical way to write this. This is a statistical way to write this. Okay, now guys, if this is the force on this wall, if I ask you what will be the pressure on this wall, if I ask you what will be the pressure on this wall, then what will be the pressure on this wall, guys? So pressure will be equal to, if I ask you pressure on a right wall, Okay, let's call it Px. That will be equal to what? That will be force per unit area. Now, can you guys tell me what will be the area of this wall? Can you guys tell me what will be the area of this wall? Anybody, what will be the area of this wall? If you look at this, guys, what is the area of this wall? Can you tell me what will be the area of this wall? What will be the area of this wall? La 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 la. Yeah, correct. The area of this wall will be B into C. Okay, so I can write Px as just equal to M divided by A into B into C. This will be just F by BC. Okay, into sigma Vix the whole square from I is equal to 1 to N. I is equal to 1 to N. This is the pressure, guys. This is the pressure on which wall? This is the pressure on this wall. This is the pressure on this wall. Okay, you know what? I am going to do what? You know what I'm going to do? What I'm going to do? I'm going to make the 3D diagram once again. Okay, I'm going to make the 3D diagram once again because that is better now. Okay, let's select this. Da, da, da. Oi, oi, oi. Da, 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 da. Da, 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 da. Control C. Da, 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 da. Control V. Da, 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 da. Okay, so now this is the pressure. This is the pressure on which wall? This is the pressure on which wall? This is the pressure on this wall, guys. This is the pressure on this wall. The pressure here is written as Px. Similarly, guys, I can also calculate pressure on this top wall. Okay, similarly, I can also calculate pressure on this top wall. Let's call it Py. What will be the pressure on this top wall? So if you do the derivation once again, okay, if you do the derivation once again, you will get Py is equal to M by ABC sigma VIY the whole square from I is equal to 1 to n. Now you might be thinking, sir, how did you write this fast, sir? How did you write this fast? This is not possible. But guys, see now, everything is always, anyways, going to remain the same. Just Ix will change to Iy. Ix will change to Iy. Okay. Then also at the same time, guys, I can also calculate the pressure. I can also calculate the pressure on this wall. Let's call that pressure as Pz. Okay, let's call that pressure as Pz. So I can also calculate pressure on this one. And what will that pressure be, guys? Once again, if you check, Pz will just be equal to M divided by ABC into sigma Viz the whole square from I is equal to 1 to N. Okay. I hope everybody understood. I hope everybody understood. Yes. Thank you, Shruti. Thank you so much. Thank you so much. See, guys, it's a very heavy derivation. It's a very heavy derivation. But I hope you guys are following so far. Okay, I hope you guys are following so far. Now, guys, what will I do? I will do something super weird. Okay, I will do something super weird. What I'm going to do is I am going to add the pressure in X, Y, and Z direction. Okay, I'm going to add the pressure in X, Y, and Z direction. So let me add the pressure in X, Y, and Z direction. Okay, one second. So I'm going to add the pressure in X, Y, and Z direction. So I will just write Px plus Py plus Pz will be equal to M divided by ABC into sigma Vix the whole square plus Viy the whole square plus Viz the whole square from I is equal to 1 to n. I is equal to 1 to n. Now guys, you have to remember two things here. The first thing you have to remember is that the speed of the first molecule can be written as under root of v1x the whole square plus v1y the whole square plus v1z the whole square. Similarly, velocity of ith molecule can be written as under root of Vix the whole square plus Viy the whole square plus Viz the whole square. This is the total speed. This is the components in x, y, and z direction. Okay, I hope everybody understood. Okay. Wow. Yeah, you will have to ask a challenger. You will have to. Okay. Now, you if you substitute this here, guys, if you substitute this here, this will just become, instead of individual components, this will just become Vi square. Okay, बहुत खतरनाक फॉर्मूला, बहुत खतरनाक फॉर्मूला, बहुत खतरनाक फॉर्मूला. Also by the way, if you see one more thing, A into B into C is just nothing but volume of this container. Okay, let's call it as capital V. So I will just substitute this ABC as just capital V. Okay, now do not get confused between velocity V and volume V. Okay, this capital V is volume. Okay, and these are velocities. VI are velocities. Do not get confused between the two. Okay, and one last thing, guys. One last thing. What is one last thing? That if you, in general, ever take 1 second, things are stuck. Things are stuck. Yeah. If you ever take a container, if you ever take a container in a real life and look at all these pressures x, y, and z individually, what you will see is that you will see something called pressure as isotropic. Pressure as isotropic. What do you mean by pressure as isotropic? What you will see is that the total pressure on the x wall will be same as the pressure on the y wall, will be same as pressure on the z wall. Pressure on all these three walls, px and py and pz, will be same, and we can just call this as p. We can just call this as P. Isotropic, not isotopic, isotropic. Isotropic means the same value in all directions. Isotropic is the same value in all three directions, all three dimensions. Okay, so I can substitute that here as well, and that will just become P plus P plus P, which is 3P. P plus P plus P, which is 3P. I hope everybody understood. I hope everybody understood. Okay, now, finally, guys, we are in the final stages of our derivation. Okay, we are in the final stages of our derivation. Finally, let's look at the definition. Let's look at the definition of RMS velocity. What is the definition of RMS velocity? What is the definition of RMS velocity? If you remember, VRMS is equal to V1 square plus V2 square plus dot plus Vn square divided by n, the whole under root. Okay, so I can just write VRMS square as equal to this. Okay, VRMS square equals to this. Now from this, I can write V1 square plus V2 square plus dot Vn square as just n times VRMS square. N times VRMS square. I hope everybody is understanding. I'm just cross multiplying this n. I'm just cross multiplying this n. So when I do this, guys, when I do this, by the way, here, what is this RHS? This is nothing but sigma Vi square. This is nothing but sigma Vi square from I is equal to 1 to n. Okay, so I can just replace this. I can just replace this with n into VRMS square. N into VRMS square. I hope everybody understood. I hope everybody understood. Okay. really hope everybody understood. Really hope everybody understood. Okay. Now, guys, in the final stages of our derivation. Okay, in the final stages of our derivation. One or two more steps. Now, let's remove all of this. Okay, let's remove all of this. I don't like this. Okay. Okay, you go. Okay, you go. And you also go. And you also go. Okay, and you also go. So let's say, guys, I had one molecule here with mass m, but here I have overall how many molecules? Here I have overall n molecules. Okay, so if I ask you what is the total mass of the gas, what if I ask you what is the total mass of the gas? Oh, yeah. If I ask you what is the total mass of the gas, total mass of the gas, so total mass of the gas will be equal to what? That will be equal to mass of one molecule into number of molecules. Do you see that? Do you see that? Yeah, just finishing up, my friend. Just finishing up. Just finishing up. Total mass of all molecules will be mass of one molecule into n, because number of molecules are n. Okay. Then, if I ask you what is the density of this air, density we will write it as rho. What will be the density? The total density of this gas will be total mass divided by volume. What will that be, guys? What will that be? That will be nothing but mn divided by v. Mn divided by v. So I can just substitute this mn divided by v with a single letter rho. I can just substitute this mn divided by v with single letter rho. This is the end of our derivation, guys. This is the end of our derivation. From this, if you do a little bit of cross multiplication, what will you get? You will get V RMS ka square is equal to 3p by rho, which means V RMS is equal to under root 3p by rho, under root 3p by rho. Okay, I hope everybody understood. This we derived just like Maxwell did, but without using his equation, we did here force analysis. Okay, we derived just like, see, I was telling you now that, oh, ho, 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 ho. Oh, ho, 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 ho. I was telling you now that there are three velocities, RMS, MP, and average. I will derive RMS, okay, and I did it within at least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 slides. Within 12 slides I did. Okay, 12 slides. Okay, yeah, it's a very small derivation, guys. It's a very small derivation. Okay. Okay, so I hope everybody understood. I hope everybody understood. Now that we are here, guys, so now that we are here, let's go one more step further. Okay, let's go one more step further and remember something else. Okay, you have this equation PV, you have this equation called PV is equal to nRT. But in ideal gas, you must have studied one more equation. Pm is equal to rho RT. Have you studied this relation in chemistry? What is P here? P is pressure, M is molar mass, okay, and rho is density, and T is temperature. Have you studied this relations, guys? Have you studied this relation? Yes, PM is equal to rho RT. Now, if you see this, then from that, if PM is equal to rho RT, I can just write P by rho is equal to RT by M. P by rho is equal to RT by M. Yes. This is for all types of gases. Fab, Phoenix. This is for all types of gases. Monatomic, diatomic, and triatomic. And if I substitute this here, guys, VRMS will now have two different formulas. It will be under root 3p by rho, and it will be also under root 3 RT by M. Okay, 3 RT by N. I hope everybody is following. I hope everybody is following. La 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 la. Now, guys, these are the two important formulas you have to always remember. Okay, every time, everywhere they will come, and you have to remember that this formula is a dhokebaz formula. Okay, it's a dhokebaz formula. Okay, I mean it's the correct formula, but from time to time, it will give you the wrong results. And this is what we call a reliable formula. Okay, Tokiba's formula and reliable formula. Now you have to remember why I will explain tomorrow. I will explain tomorrow why one of them is Dhokebaz and the other one is reliable. I will explain tomorrow. Today, I will just stop here, but I will not go before giving you one homework question. Okay, today we don't do any questions. So, Dhokebaz, by the way, means baseman. Dhokebaz means unreliable. Okay, Dhokebaz means someone who can stab you in the back. This formula will stab you in the back. Okay, so do not trust this formula. This is an untrustworthy formula. This is an untrustworthy formula. Do not trust this formula. Always trust this formula. Always trust the second formula. Okay, yeah, I know. Okay, guys. So let's talk about Vedantu's platform for JEE and NEET. Let's talk about Vedantu's platform for JEE and NEET. It's the best if you're preparing for JEE or NEET and you're in class 11th or 12th. If you take the pro subscription, guys, you get 5,000 plus hours of online teaching. Okay, you get full access to all the live courses. You get full access to all the live courses where all subjects are covered in great detail. You get to choose the language, English or Hindi, in which you want to study. You have instant in-class doubt solving where you get to study from India's best teachers, all of them having 5 plus years of experience. Okay, instant in-class doubt solving means what? If you have class teachers there. Okay, but they're just to solve your doubts, nothing else. Okay, and you get to learn safely from home on any device you want. So how do you get the pro subscription, guys? You have to go to vdnt.in/ytpro. Go to vdnt.in/ytpro and use my coupon code AAPPRO. When you do that, guys, you get additional 15% discount. When you do that, you get additional 15% discount. Go to vdnt.in/ytpro. Okay, now if you haven't joined our Telegram group, guys, please join our Telegram group. I'm going to post the notes there. Other than that, we have assignments and quizzes and everything posted on this group only. So please do that. Please do that. Also, at the same time, guys, if you are still with me so far, let's give you one homework question. Okay, this is the homework question. Please write the answer in comments. Please write the answer in comments. Okay, the density of a gas is this, the root mean square velocity of the gas is this, the pressure exerted by the gas on the wall of the vessel will be what? Okay, it's very simple. It's very simple. You just have to use one formula. Give me the answer in the comments. Okay, Smartbook is asking for assignment answers. Smartbook, yes, I will post the solutions to assignment also very soon. Post the solutions to assignments also very soon. Don't worry. Okay. All right. Yes, Nina, I have one more class at 3:30. Okay, one more class at 3:30. So no issues. So guys, I have to end the lecture today because I have one more class as well. Okay, I have one more class as well. It was so fun to teach you guys today. And thank you so much. You were so patient to stay till the end. Oh my god, I can't believe you did that. Okay. See, in general, when I teach this in class, students don't have a choice. They can just go out of the class anytime they want. But you stuck by. You could have left, but you stuck by, and that's why you are awesome. Okay. Yeah, that's why I love you guys, seriously. So thank you so much for sticking by till the end. This was a very difficult topic to teach because it has just a lot of derivation steps. There are 12, 13 steps. But you stuck by. Superb, guys. Superb. I love you. Okay, so I will end this class here today and I will see you guys tomorrow. Okay, and I will post the notes at around 4:45 p.m. Do not worry. Shravani, I will post notes. Do not worry. Okay, chalo guys. Have a nice day and bye.